Imagine trying to find a single needle in a haystack so vast it stretches across continents. Classical computers would meticulously check each piece of hay one by one. What if there was a way to check all of them at once, almost instantaneously, to find that needle? Oracle problems drive quantum speedup by presenting computational tasks in a specific structure that quantum computers can exploit with their unique abilities. This structure, often called a black box function, allows quantum algorithms to query many potential answers simultaneously, leading to significantly faster solutions. In quantum computing, an oracle is essentially a subroutine or function whose internal workings we do not necessarily know, but which we can use to evaluate an input. A classical computer, when faced with such an oracle, must typically query it sequentially, one input at a time, until it finds the desired information. Quantum computers, however, can prepare a superposition of all possible inputs and then query the oracle with this superposition just once. This single query effectively processes all inputs in parallel. The magic happens through quantum phenomena like phase kickback or amplitude amplification, which subtly encode the oracle's output into the phases or amplitudes of the quantum state. This allows the quantum computer to extract global properties of the oracle with far fewer calls than any classical machine. So, how do we identify or apply these problems? An oracle problem exists whenever we need to learn a property about an unknown function by simply evaluating its inputs and outputs. A classic example is Grover's algorithm, designed to search an unsorted database. Here, the oracle is a function that identifies the target item we are looking for. Another instance is the Deutsch-Jozsa algorithm, where the oracle determines if a binary function is either constant for all inputs or balanced, meaning it gives a 1 for exactly half of its inputs and a 0 for the other half. In both cases, the quantum algorithm gains its advantage by asking the oracle questions in a superposed state, efficiently revealing the answer without examining each input individually. The core idea behind an oracle problem is that the quantum computer does not need to understand the internal logic of the function. It just needs to interact with it as a black box that transforms input states. This means the speedup is not about making individual computational steps faster, but about dramatically reducing the total number of queries or computations needed to gain specific information. However, it is important to remember that the design and implementation of an efficient quantum oracle for a given problem is often a significant part of the challenge itself. Ultimately, oracle problems are the perfect playground for quantum speedup because they provide a framework where quantum superposition and entanglement can shine. By framing certain computational tasks as oracle queries, we can unlock the potential for exponential or polynomial speedups. This transforms difficult search or decision problems into manageable ones, paving the way for advancements in fields from cryptography to materials science. It is a powerful demonstration of how quantum mechanics can fundamentally change the way we approach computation.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.